So now our next talk will be presented by Professor Moncef Nehdi. He's a professor and the chair of Department of Civil Engineering, McMaster University in Canada. Professor Nehdi was a professor at Western University and associate director for environmental research of Western. He is a fellow of Engineering Institute of Canada, ACI, Canadian Society of Civil Engineers, received several awards, and he is ACI award for professional achievement and many other awards. He chair of the ACI Committee 555 of recycled materials. His research focuses on sustainability and resilience of the built environment, computational intelligence modeling, and innovative materials for construction and energy storage. Professor Nehdi will give us a talk about predicting the future of creating it. Systems thinking approach to concrete sustainability. So please, Dr. Nehdi.
Thank you very much for the very kind introduction, Ahmed. Welcome everybody, wherever you are around the world today. I hope you're doing well, staying healthy and positive. I would like to thank the organizers for putting together a very nice virtual symposium. An amazing lineup of speakers, great talks. I must admit that some of the speakers today were perceived as legends in the field since I was a graduate student. So some of them are actually my mentors and teachers. And to be part of this today, I perceive that as a privilege, and I feel lucky to participate. As so well put by Isaac Newton, if we can see that far, is because we stand on the shoulders of giants. When I see some of those speakers going to retirement, such as Surendra Shah and others, I always worry who's going to fill in their shoes, and I get always surprised with fantastic emerging scholars who come up with very innovative ideas and research. So I think our field is in very good hands. When I got invited to be part of this virtual symposium, I initially thought about talking about some laboratory research that we do, or even involvement in field work, where we try to implement, sustainability concepts and CO2 reduction and so on. But then it came to my mind that due to the heavy involvement of MIT into this event, probably the best thing I could talk about is something I learned from MIT, specifically from people at the Sloan School of Management. So my talk a bit shifts today from the great technical content that was discussed so far, maybe shifts gears a bit more towards the policy aspects. And my main goal here really is to try to send a message to the great audience of early career researchers and students who are attending today, just to say that sustainability of cement and concrete and the issue of CO2 emissions and all that is a very complex system of systems. It captures and includes social, economical, and political issues. And those are actually much more complex to model and predict compared to engineering systems. They tend to be highly nonlinear, governed by multiple time-dependent feedback loops. And therefore, the use of mental models is futile. We tend to think linear, we tend to think deterministic. And I'm trying to just capture through this presentation why the policy aspect of this discussion is also very, very important. Now, as a university researcher and academic, I'm supposed to work on my, Mickey Mouse projects in the lab, and maybe sometimes talk about some field implementation pilot projects and so on. But for some reason, maybe serendipity, I had the chance to be involved in some world landmark projects. For example, the Mecca Clock Tower, which stands right now as the world's third tallest building, the building with the largest floor space on Earth, the tallest hotel, and so on. It has many world records. I was involved also in the Al Jamarat Bridge, which is perhaps the most venerated pedestrian bridge in the world, with multiple floors. It can accommodate about 250,000 of pedestrians per hour. I got involved in the Haram expansion project. This probably breaks a lot of records in self-consolidating concrete technology. I designed the concrete for this North Jeddah water treatment plant, which stands as the deepest and the second largest in the world. The King Abdulaziz Airport, which is expected to become the world's largest airport. The King Abdullah Financial District in the city of Riyadh. Tremendous logistic nightmares, like you're building downtown Chicago at the same time. And the early stages of the Kingdom Tower, which is supposed to be the first building on Earth to exceed 1 kilometer in height. In all these projects, I had a chance. I took 3 years of leaves from the university, and I used to travel on average 1 month to 2 months per year to get involved in these projects. And I had the first-hand chance to actually try to influence sustainability. We have done what we can. These projects stretch the capabilities of our design codes, stretch the capabilities of our engineering concepts, and so on. So, we did things like using 45% fly ash in some of this work. These are multi-billion, multi-million cubic meters of concrete, but we didn't have fly ash there, so we had to import it from India and South Africa, and that comes with its challenges. What I have realized in these is that the policy issues sometimes become the barrier against implementing, sustainability measures. For example, just, for the Kingdom Tower, I did initial tests on the concrete to try to meet the modulus of elasticity of the designer, which was calculated as per ACA 318. And that equation overestimates any modulus. You can increase the strength as much as you want. I think Surendra Shah talks about that issue early in the morning. So there are multiple challenges. Now, in terms of policy, the concept of sustainability, sustainable development on its own is revolutionary, but it remains to be difficult to be tangible and to quantify. Engineers like, when I talk about this to my students and colleagues, engineers like to quantify things, talk in numbers. So it remains as a vague, vague and not tangible and ambiguous concept, and therefore did not allow to create a real paradigm, an operational framework for really implementing the policies to lead to meaningful results. So the policy making aspects are incredibly important in what we do. I mean, we heard a lot about amazing technical results and so on going on, but I think we have to put this in the frame of policies. And I will not spend too much time on this, but the issue of climate change started probably the issue of sustainability perhaps emerged in 1972 in the first Earth Summit in Stockholm, where the declaration raised the issue of climate change for the first time. It took until 1987, where the UN General Assembly adopted the environmental perspective for year 2000 and beyond, which introduced the notion of sustainable development. However, it was a bit disappointing. It's a very big document, but it just put the issue of climate change as a small item under the policy directive related to energy. 1988 saw the Panel on Climate Change emerging, IPCC, was created and met for the first time. And this is a forum for examining the greenhouse warming, global warming issues and climate change related considerations. The real year of, you could call the watershed or the landslide of policy on climate change was 1989, where global change was brought forth to the far front of the policy agenda. And it became a prominent international public debate issue. The UN General Assembly identified as a specific and urgent issue. There was a declaration that called for preparations for negotiations to create a framework and so on. There was the Mali Declaration, which pertains to global warming and sea level and so on, the Helsinki Declaration and the Montreal Declaration, which both focused more on ozone layer and so on. Now, 1990 was the Second World Climate Conference. And again, here the issue of climate change was further emphasized, and there were calls for negotiations again and underlying the urgency and so on. And then the Rio de Janeiro General Assembly of the United Nations, which added further aspects with about 158 states joining to sign a declaration for trying to now pursue meaningful results in terms of curbing CO2 emissions and climate change issues. Then there was the Berlin Mandate, and then which is called the Conference of the Parties, COP1. Remember this COP1 term, because now we stand at COP26, and then there was COP2 in Geneva. The Kyoto Protocol is COP3, where there were quantitative targets. Here we wanted to reduce CO2 by 5% below 1990 levels, etc., etc. So now we stand at COP26. The most recent was organized in Glasgow, Scotland, last October, November. And if all these 26 COPs had a purpose of creating an exponential growth in CO2 emissions around the world, they wouldn't have been more successful. Because actually, when you look at the curve here, that's exactly what has been happening. Why are we failing? Why we keep failing like this? Why we have organized all these conferences, we emitted all these policies, all these agreements, signatures, and so on, only to attain a result like this, where the CO2 emissions keep increasing, climate change is turning into an existential threat to humanity. Looking at the global temperature, I mean, it's escalating, and this is not, again, not linear. You have the ice cap melting, but then the ice cap is not reflecting enough solar energy as it used to be before. You get things escalated, becoming really, really dangerous. Now, looking at our own turf, the cement and concrete industry, I mean, the construction industry is a big participant to all of this. It's the third largest source of anthropogenic emissions of carbon dioxide after fossil fuels and land use. And if you consider it as a country, it would rank third after China and the United States in terms of carbon emissions. And if we look at what we have achieved with all these policies and attempts that we have been making, two-thirds, maybe more than two-thirds of CO2 generated from cement production have been produced after 1990, which is the peak of policies for reducing CO2 emissions. So it is a tremendous challenge. It is a tremendous challenge, but it's also a tremendous opportunity. There are predictions that the CO2 market is set to reach $600 billion of annual revenue. That is gigantic. So there is tremendous opportunity there for making change. When we look at the situation, cement production has been increasing, obviously population growth and urbanization, the development of countries and so on. So you see cement production, those orange bars increasing with time. And you see the lighted shaded part of the curve, that is the ratio of CO2 emissions over total CO2 emissions. And that ratio is not either decreasing. It used to stand at less than 4%. That has escalated to maybe 8, some places maybe 9, 10, and so on. So how can we reduce CO2 emissions from cement and concrete by 50% in the next 10 years and reach the net zero by 2040 or 2050? How can we do this if this is our track record? Now, if we don't pay attention to the policy issues, are we going to end up with the same results that we have had in the past? Now, we should not deny that there have been tremendous progress made, since the modern cement kilns, which reduced maybe the energy of producing cement by 1/3 or so, the attempts for clinker reduction using supplementary cementitious materials, alternative supplementary cementitious materials. We had several talks on that today, effective admixtures and so on. The contribution of standards, guidelines, design codes, which can shift concrete productions toward more sustainable practice. But there are many other opportunities that have been exploited and have not been fully exploited yet. Alkali activated materials, though they can occupy a smaller market share. We heard Karen Scrivener talking about LC3 and LC2, the CO2 curing and the carbon sequestration. And we heard Kei-Jun Shi also touching on that. The aspect of mineralization, that is capturing CO2, for example, to make aggregates, and all the material sciences aspects, such as what Nehdi Bantia talked about today. The contribution of artificial intelligence, where we can actually provide more predictive tools to design concrete mixes with lower carbon content. And yet, transformative, truly disruptive solutions have not yet been developed. As Karen Scrivener said, there is no silver bullet. And therefore, what disturbs me is that when you look at some significant part of the literature on cement sustainability and concrete sustainability, it amounts to what you could call greenwashing. You know, and I think the main reason for this is that the big picture is not being captured. You see research talking about something, and then the conclusion is this has the potential to reduce CO2 emissions from cement production by 500 million tons. Come on, I mean, if you implement that material that the research is talking about on the entire Earth, it's not going to lead to any close numbers to that. So there is a lot of R&D money spent, some rosy claims, but the impact very often is limited. So this is not about us publishing more papers and getting more recognitions and so on. This is about the fate of humanity, and therefore we need to really do things that are impactful, that capture the real picture, that capture the complexity of the problem. Now this figure here on the left, I extracted that from my daughter's, you know, elementary school textbook, and that's how sustainability is being, you know, presented to the young students. Barry Richmond, one of the great minds of system dynamics, calls this the laundry list thinking, So looking at the industry practice on the right hand of the screen, you see something that is not quite very different. The top figure is about geopolymer concrete and how sustainability issues are captured, and the bottom one is about the embodied energy and carbon through a life cycle of a building. And you don't see tremendous differences between those diagrams. Why? Because we have not captured the complexity of the problem through systems thinking. Let me give you an example to just make this very simple and tangible to all the students that are listening today. Let's say somebody says sales are bad because marketing is inadequate. You know, you could say after that, well, marketing is inadequate because salespeople are not motivated. And then you can follow that logic and say salespeople are not motivated because of this or that. So you can see that through mental models, we can always find another event that caused the one that you initially thought it is the cause. So mental models do not see the complexity of interrelationships and time-dependent feedbacks. Mental models tend to be fuzzy, they're incomplete, imprecise, and they change with time. They change within the same debate. You talk with a person within the same debate, their mental model can change. And therefore, such models cannot handle the multi-loop, non-linear feedback systems for which the tools that we use, contemplation, intuition, discussion, guesswork, all that is futile. It does not work. So just to make that even more, you know, schematic, you know, the laundry list thinking is the person here saying, well, I'm glad that the hole is not on my side of the boat, or somebody sitting here pushing that side, thinking that it doesn't affect the other side. Systems thinking sees the interrelationships between things and the complexity of things. So this looks a bit complex, but if I take my daughter's, you know, diagram about sustainability on the left side to the right side, where I schematically represent a causal loop diagram, where parts in the system influence each other through time-dependent feedback loops. That looks complex, right? How can you think about that? You know, it's very, but actually, when you start learning systems thinking and system dynamics, that approach becomes a second nature to the way you consider things. So what is systems thinking? Very quickly, in very brief terms, in very simplistic terms, it's a holistic way to investigate factors that and interactions that could contribute to a possible outcome in a complex system. So it sees holes and patterns rather than static snapshots as the mental models would perceive things. It focuses rather on the interrelationships and not on the things. So for example, take the issue of CO2 emissions from cement production. That's a complex system and has a high degree of feedback among its components. And if you don't account for such effects, then the policy making that you do through the industry and through the design codes and all of this can be futile at the end. Here's another example to make it even simpler. So for example, take traffic congestion. You know, we have a neighborhood where we get a lot of traffic congestion. Traffic is terrible. So the mental model to solve this would say, all right, let's build a new highway. Let's build a new road. And once that's done, you know, after a while, that policy fails. So now you're facing the dilemma that you're spending public money to solve problems. And we do this we see this a lot with our politicians. And it turns out the problem to be worse. Why is this? It's because we don't capture the feedbacks. So now you built a new highway, the initial traffic volume becomes very low. It becomes nice to travel there. The neighborhood becomes very attractive. People say, hey, wait a minute, I can buy my car. I don't need public transit, you know, and the developers say that neighborhood is very attractive. Let's build more houses and so on. And then eventually the problem that you wanted to solve becomes a bigger problem. Take another example. For example, there is a neighborhood in town that has a lot of poverty, a lot of homeless people. So the mental model will say, okay, let's build a lot of, you know, social housing there. And they build a lot of social housing. Initially, the problem looks like solved. What happens next is that area becomes very, very attractive to low-income people, and you get more people coming in there, you know, with possibility of increased level of crime and so on. Investors who had businesses there, they say, wait a minute, I don't like this neighborhood anymore. They move somewhere else. And then you wanted to solve a problem through a mental model, you created a bigger problem. In contrast, system dynamics, what it does, it captures those feedbacks. It implements those feedbacks in the policy making, and therefore the complex endogenous variables that will surprise you, they will be accounted directly inside the structure of the model itself. And how we do that? We do that through what we call the causal loop diagram. Here's a simple causal loop diagram for the traffic congestion that I talked about earlier. This is not by any means comprehensive, but it captures population growth, how many cars in the region, how many cars per person, what's the situation of public transit, you know, the adequacy of the public transit, what are the desired times there, what are the pressures to reduce congestion, what's the highway situation, and so on. Through such a program or such a layout, you see those positive and minus signs that you see there. I'll explain those a bit later. We try to capture the complexity of the problem. Now, systems thinking and system dynamics, they're essentially grounded in the work of J. Forrester at the MIT Sloan School of Management in the late 1950s. J. Forrester was initially computer engineering. In fact, he contributed to the development of memory storage and so on, but he's also credited to be the father of systems thinking. What's the difference between systems thinking and system dynamics? Because I keep mentioning the two terms. Well, they're kind of the two sides of the same coin. Systems thinking focuses more on exploring the interrelationships, the creating causal loop diagram. Systems thinking is something you can do on a piece of paper with a pencil. System dynamics takes that to a higher level. Barry Richmond is credited for taking the system dynamics from an academic environment to the business world through the creation of, for example, the program Stella. And there are other programs like Vensim and so on that do this on a computational level. So what these systems do, they try to capture feedbacks. And feedbacks in a system, there are many different ones. I don't want to spend a lot of time on this, but you know, systems thinking captures feedback such as, you know, for example, you have a population of bacteria with nutrition. The bacteria will grow very, very rapidly, and then when they consume the bacteria, there is an overshoot and then a collapse of the population, and things like that. Take an example of when you open a water tap to fill a container. So your eye has the control policy for your hand to open the tap, And then you keep observing, so there is feedback, there is time-dependent feedback. You're looking at the water filling, the stock, which is the bucket here, and then sending information to your eye. That is what system dynamics try to do on a rather more complex system. How does it do that? Well, beyond the causal loop diagrams, you can build the sustainability model for CO2 emissions, for example, through simple building blocks, which essentially are shown here in a very simplistic way. First, connectors. Connectors here, they essentially represent, they are represented through arrows, and they represent the relationships between elements in the model. The stocks are where things accumulate or where things are spent from. For example, how much cement is being produced, and it's represented through those blocks like squares or rectangles. And then you have the converters, which are represented by circles, and essentially those are math operations or algebra, how parts of the system influence each other. And then you have the flows, which are basically representative of quantities. They are represented as something like a tap there, like the rate, for example, of cement consumption and things like that. Using these building blocks, and I did mention that I will mention the plus and minus sign. So when you see plus sign, essentially more of the same thing produces more of the other thing, or less of the same thing produces less of the same. For example, if your self-esteem goes up, you accomplish more. If your self-esteem goes down, you accomplish less. The negative sign is if something goes more, then it produces a negative effect. So the more you spend, the less you have in the bank, kind of thing. Now, taking this to a more practical level, let's say this is a simplistic model for the effect of alkali activated materials on CO2 emissions. So this sounds like a simple system where you have precursors and activators and mix them and so on, produce something. And then how many cubic meters you're producing, how much CO2 being reduced. But it's not like that. There are multiple issues that are influencing each other here. The concrete the durability, the economy, how much construction is happening, the availability of materials, the durability aspects, the carbonation, the CO2 emissions, all this. You try to capture that through a model that looks like this in terms of causal loop diagram. And you take it further. You take it further to a system dynamics model, for example, in a STEALLA environment, and you try to build your model now, and now you have to come up with rational, mathematical relationships that demonstrate or capture the effect of different parts of the system on each other and versus time and so on, which is the quite challenging part of creating the model. Now, when you look at this model, it looks simplistic, but parts of that model are also sectors. So there are multiple sectors influencing each other. For example, you see on the left here, the carbonation sector. You see on the right, the CO2 emissions sector. And here you see the alkali activated materials composition sector. So using such sectors and such building blocks in a system dynamics model, we can create something for policy making. Now, let me just be transparent here and very frank. Policy making is not about predicting the future. It's not about saying 2069, corrosion is going to start. It's not like that. It's a tool for policy making, and therefore it's built on assumptions. For example, one of the things you see in these results, and these are just simplistic simulations, what is the time of policy implementation? You see the curves are one curve in the beginning, and then they diverge from each other. That's when the policy gets implemented. So if we want, for example, to replace 20% of Portland cement with LC3 over the next 10 years, when that policy is going to start. That's not enough. How's the economy at that time? What is the trend of population growth in the next 50 years? How the economy is going to evolve in the next 50 years? What are the pressures and policies? How the climate change impact is going to be on humans and all that? And multiple assumptions like that will give you different policy trends. So system dynamics is a way essentially for capturing complex systems, and it's a way for policy making. What it adds to the picture is that instead of thinking linear, thinking simplistic, thinking deterministic, once you capture the complexity of the problem through causal loop diagrams and through system dynamics modeling, you got more realistic predictive trends of the future. Now, we have done a bit of work on this. So we published, for example, system dynamics model for sustainable cement and concrete novel tool for policy analysis. Another one is policy making for greening the concrete industry in Canada, systems thinking approach. Third one is estimating CO2 emission savings from ultra high performance concrete system dynamics approach. The fourth is mitigating Portland cement CO2 emissions using alkali activated materials, system dynamics approach. My dream challenge now, because I do a lot of computational intelligence and artificial intelligence modeling prediction, if I can couple artificial intelligence with system dynamics, I think I will need another 10 or 15 years to do this, but it's quite a challenge. Now, I want to invite you to study this further. I think we have a lack of literature in this domain, and many of the young students and researchers listening today probably can have significant contributions in this field that is under-researched. So you could look at, for example, at publications of Jay Forrester, who's, as I say, the pioneering American computer engineer, who's the father of system dynamics. Barry Richmond's publications, he's a PhD graduate of Jay Forrester. He took that to business level, creating the High Performance Systems Incorporated, the company that developed the Stella and I think modeling approaches. And as I say, there are other systems for system dynamics modeling, such as fencing and so on. And John Sterman is actually still at MIT, Sloan School of Management, and he's the director of the MIT System Dynamics Group and the MIT Sloan Sustainability Initiative. There is a website for system dynamics, for the System Dynamics Society, which is a great source for information for those who want to study this further. So maybe I could try to make it brief by touching base on some concluding remarks. So I remember one of my great mentors who taught me when I started making long and boring presentations. He told me, listen, Moncef, a presentation is not intended to impress people by how much you know. It's intended to get people interested to know more. And therefore, you make it short and invite them to search for more information, reach out to you or to others, basically, because the topic seems to be interesting. So that is what I'm trying to achieve here. So yes, strategies and policies deployed over the last several decades to decarbonize the economy have by and large failed. There are some limited successes, but the outcome essentially is that climate change has risen unabated to become an existential threat. We see symptoms of that around the world, extreme weather events, so many more abundant wildfires, more frequent hurricanes, more frequent droughts, rising sea level, melting ice cap, changing, dynamics of plants and animals and so on. It's a tremendous challenge that is coming our way. For our specific case of carbon emissions from cement and concrete, I believe that the fragmented view of the problem, by looking at the issue from a very narrow angle, has led to mitigative schemes that did not work sometimes. Could be just simply greenwashing, as I said earlier, though there are many serious efforts that are to be commended around the world to make real impact. And the sustainability of concrete is a complex system of systems. It has time-dependent feedbacks and different parts influencing one another within the multifaceted whole. If we do not account for the social complexity, for the economic complexity, for the policy complexity of the problem, we won't solve the problem. So as I said earlier, I've seen some research talking about a tool that can barely be implemented in 10% of cement and concrete production in the United States, stating that this was going to decrease CO2 emissions in the world by 500 million tons. That is not really realistic. So systems thinking perspective to tackle the problem, I see it's essential. The application of system dynamics better captures the complexity and captures the outcomes of policies for reducing carbon emissions from cement production. and the sometimes counterintuitive behavior of the system. We have had 26 COP conferences only to make things really much worse. The intricate social, environmental, economic, and technical aspects of the problem need to be addressed in a holistic manner to yield meaningful reductions in carbon emissions. So at the end, I believe that we need policy, action, research that really capture the complexity of the system, that are truly impactful, that produce meaningful results before it really gets too late. With that, thank you everyone for your attention, and I will be very happy to listen to your comments or answer any questions if I can. Thank you very much again.
Thank you, Professor Moncef, for this informative lecture. I have here one question. Says, how can the supply chain management affect creating sustainability development policies?
This is a question that can be captured very well when you look at the causal loop diagram of the sustainability system within the cement and concrete industry. So it is an important sector of a bigger picture. How exactly it does? Well, it's going to depend on a number of assumptions. It's never certain. You could look at the current situation of supply chain, how much materials are available, where are they available, are they economically attractive to be used to create sustainability solutions? Is there sufficient incentive and stimulus for the stakeholders to adopt these? So it's a complex thing, it's a complex question. And if I answer you now, I'm going to give you a mental model that is wrong. So I need to run a simulation.
Okay, thank you so much. So just like everyone is thanking you for your presentation, and also I concur with, this is very good presentation. Thank you so much, Professor Nehdi.
That's been a pleasure. Thank you very much. Appreciate it.
So I hope you're still not very tired by going during the day. So